Okay guys, so we're looking at the notes today for section 2.6. We're doing related rates, number 3 notes. On this section, we're going to be looking at spheres and the relationship between spheres and their volume. We're also going to be looking at cubes, and we're going to be looking at the volume and also the surface area. If you look at your green sheet, on the front of it, there's a section that has geometry formulas. Rather than having you memorize all of those formulas, I have them on there for you to use, and it'll probably be helpful, especially for some of these formulas that you may have forgotten. So for the first problem, it says the volume of a spherical balloon is increasing at a rate of 3 inches per second. First of all, there's a little something wrong with that statement. Does anybody know what's missing there? Cubic, right. It's going to have to be inches cubed per second, because volume is measured in cubic units. Then it says find the rate of change of the area, and that word should not be area, it should be radius, with respect to time when r is 2 inches and then when r is half a foot. Alright, so the first thing we always want to do is we need to find the formula. So we read through the problem again, the volume of a spherical balloon. So volume of a sphere. Do you know the formula for the volume of a sphere? Good job. So V is going to be 4/3 pi r cubed. After we have the formula, now we have to take the derivative. A lot of you get confused about whether you're taking the derivative with respect to x or with respect to t. Those are the only 2 things we take the derivative with respect to. So this says right here, with respect to time. So what are we taking the derivative with respect to? T. So here's our derivative. The derivative of v is just going to be 1, but it's going to be 1, and then what do I have to put after it? dv dt. Good. For this derivative, it's 4/3 pi r cubed. Well, the 4/3 and the pi are just like a coefficient. So I have to multiply the coefficient times the exponent. What do you get if you multiply the coefficient times the exponent? 4 pi. Then we put our r is a variable, and then we have to subtract 1. So it's 4 pi r squared, and then what do I have to put after it? dr dt. Good. So now we go back, we skim through the problem. The volume of a spherical balloon is increasing at a rate of 3 cubic inches per second. So is this 3 going in for r, dr dt, or dv dt? What is it? The volume is increasing at a rate. That's dv dt, isn't it? So dv dt is going to be 3. 4 pi. They tell us the radius is going to be 2. So 2 squared. And then, reading the question again, find the rate of change of the radius. So that's good. That's what we're trying to solve for. So I have 2 squared is 4. 4 times 4 is 16 pi. So I've got 3 equals 16 pi dr dt. So dr dt then for this problem is going to be 3/16 pi, and that's going to be inches per second. What I see a lot of people do is they put this pi in the numerator. That's wrong. You cannot write it like this either. A lot of people do this, 3/16 pi. They write it like that. See how that pi, that's really in the numerator, and the pi must be in the denominator. So be careful with things like that. For part B, we're doing the same thing. We're not going to bother writing the formula, finding the derivative. We already did that part. The only change is now we're talking about the radius being half a foot rather than the radius just being 2 inches. So we go to our derivative part, and we've got dv dt is still going to be the same thing. It's still 3. 4 pi. The radius is now half a foot. Am I going to put in a half for r? What are we going to put in? 6. So we're going to have 6 squared, which is 36 dr dt. Don't get out a calculator to multiply 36 times 4. Just do 36 times 2 is 72, and then times 2 again. There you go. Anytime I'm multiplying by 4 or by 6, I multiply by 2 and then by 2 again for 4. If I'm multiplying by 6, I multiply by 3 and then I multiply by 2. It's just faster. So now dr dt.
Teachers, please excuse the bells.
Okay, so we've got this, and this is going to be inches per second. Okay? Questions there? All right, let's look at the second one. A cube has edges that are decreasing at a rate of 2 centimeters per second. How fast is the volume changing when each edge is, first of all, 3 centimeters and then 1 meter? Well, this room we're in, this is close to being a cube. It's pretty close, okay? Needs to be a little bit higher walls. But to find volume, volume is just always area of the base times height. So what's the area of the base then? This is a perfect square base, it looks like. So it's going to be x times x, which is just x squared. And then if the height were the same, it'd be x squared, x cubed. And if you look at your geometry formulas, right here it is, volume of a cube. All right? So we're going to write down that's our formula. Our formula is v equals x cubed. Then we have to find our derivative with respect to t. So the derivative of v with respect to t is going to be just 1 dv dt. Derivative of x cubed, what's it going to be? Good. And now we go back and read the problem. How fast is the volume changing? That's dv dt. I always like to circle what it is I'm looking for. And it tells me that each edge is going to be 3, so I'm going to plug in 3 for x. So it's going to be 3 times 3 squared. dx dt is decreasing at a rate of 2 centimeters per second. So what do I have to put in for dx dt? Negative 2. I'm going to call this v prime now, just to make it a little simpler. 3 squared is 9. 9 times 3 is 27. Times 2 is 54. So for... What's that? I'm just calling dv dt v prime. It means the same thing. And then I'm saying I plugged in 3 for x, because that's the length of the side. dx dt was the rate of change of each edge. So that's why dx dt was negative 2. So then our v prime is going to be 9 times, that's negative 54 centimeters cubed per second. Guys, watch your units too. I always go back and check this. Volume, cubic centimeters per second. Make sure you have the correct units. Part B, it says for 1 meter. Well, we already have our derivative, so I'm not going to bother finding that again. So we're going to have now v prime equals 3. I have to plug in 1 meter, but everything else is in centimeters. So what's 1 meter in centimeters? 100. There's 100 centimeters. You are going ahead, I know. So it's going to be 3 times 100 squared, and then times negative 2. And if you don't know that, guys, on your green sheet you can even write that. 1 meter equals 100 centimeters. And so v prime then, I'm going to do 100 squared. That's going to be a 1 with 4 zeros. We get twice as many zeros. So it's going to be 3, 1, 2, 3, 4 30,000 times negative 2. So it's going to be negative 60,000, and that's going to be centimeters cubed per second. Okay? Why is this V prime negative? What does that tell me about the volume? It's decreasing, yes, that's all that means. Alright, let's look at example 3. It says the conditions are the same as in example 2. How fast is the length of each edge changing when the surface area is changing at a rate of 36 square centimeters per second? So how fast is the length of each edge changing? So you may want to jot down that what you're trying to find is dx dt. So this is telling us the rate of change of the surface area. So we need to know the surface area of a cube, because it's the same type of shape. It's still supposed to be a cube. So you're going to have to look at your paper, or maybe, hopefully you know. Think about this room, guys. The area of the floor is x squared. The ceiling's x squared. That's x squared. That's x squared. Front and back are x squared. 6x squared. So there's our formula for the surface area of the cube. What's the derivative of s going to be? This derivative is going to be 12x dx dt. Let's see what we're going to substitute in. How fast is the length of each edge changing when the surface area is changing at a rate of 36 square centimeters? So this right here is 36. And then we're just going to go ahead and use the condition up here that we're using 3 centimeters as the length of the edge. And we're trying to find how fast each edge is changing, so that's dx dt. That's what we're trying to solve for. Everybody see why? We're not using this condition that the edge is decreasing at a rate of 2, because that's what it's asking us to find, is how fast the edge is changing. So then what are we going to get for this? Yep. So dx dt, or if you prefer to call it x prime, is just going to be 1. So 1 centimeter per second. Okay, any questions? Alright guys, so instead of doing what's on your assignment sheet, I did change that second page. I want you to do 4, 7, 21, and 48. That's going to be a really good review for your quiz on Monday. I will also work out all of those problems and put them on Canvas so you can look at them and study before you come in here on Monday. But just remember, half the quiz is over finding the derivative with respect to x. The other half is finding the derivative with respect to t. Read the problem to figure out which you should be doing. Okay?